Hello, in the previous video we looked at the derivative of the absolute value function. In this part we're going to apply it to a trickier example, and this is for learning intention 14. So a question might look like, given f of x equals the absolute value of x squared minus 1, find f dash of x. Alright, the first thing I want to do is give you the graph so you can see what the graph looks like of x squared minus 1, the absolute value of it. So the graph looks something like, and you can find this out using DRT and the four labels. I've got this called symmetry thing here. The graph will look like this. There we are. And if you go through and find these points, that's going to be negative 1, 0. It's going to be 1, 0. It's going to be 0, 1. There's our graph of f of x. How do we find f dash of x? We do it by making this into a piecewise function. So we write f of x equals, well, how do we get that into a piecewise function? Let's remember what we did in the last video. In the last video we had f of x equals the absolute value of x. So we said that we could rewrite that like this. We could rewrite it as equals x if x is greater than or equal to 0, or it equals negative x if x is less than 0. Well, we can use this different representation to rewrite this. This argument here, this x, just goes to those four places. Can you see that? So you can rewrite this by taking the argument x squared minus 1 and just popping it into those four positions. Well, okay, so it will give us x squared minus 1 when x squared minus 1 is greater than or equal to 0, or negative x squared minus 1 when x squared minus 1 is less than 0. Can you see how I've taken the argument of the absolute value function and subbed it into the piecewise function? Let's tidy it up a bit. So you get x squared minus 1 if x squared minus 1 is greater than or equal to 0, or 1 minus x squared. So here I'm just expanding the brackets. If x squared minus 1 is less than 0. Well, that's good because we can find the derivative now. So the derivative f dash of x equals 2x, and the derivative of that is negative 2x. And I should really write ifs here. Makes it look a bit nicer. If. So if, well, it equals 2x if some condition, and negative 2x if some other condition. The way I like to think about it is over on this graph here, this part of the function is unaffected by the absolute value on the outside. You would get this part anyway, wouldn't you? So that must be the part that has the derivative 2x. So we can describe that that domain for that section. So it equals 2x if x is less than negative 1 or x is greater than 1. Down here, I'm going to call this the blue part. Well, that must be what's remaining. So it must be this part. So that must be if x is between negative 1 and 1. Notice how I'm not including negative 1 and 1, because the derivative is not defined at those cusps, or those vertices, whatever you want to call them. The derivative is not defined there, so I can't include it here. That is your answer. and that's using a graphical approach. I think that's the best approach. As an exercise, if you like, if you solve the inequality x squared minus 1 is greater than 0, you'll actually get this answer, almost. And if you solve x squared minus 1 is less than 0, you'll get this answer. The only difference is you still have to look at the graph to know to get rid of the include sign. So that's why I prefer a graphical approach, because you're going to look at the graph anyway. So as an exercise, try solving these two inequalities and see if you get these two respective answers, but also make sure you can handle it graphically. And if you have been, thank you for watching.